Hello to everybody. We have with us Fulvio Melia for the third time in our institute. I think he likes very much to come to Tenerife, and possibly he will come again. He was doing a PhD, the undergraduate students in Australia. He comes from Australia, and then he was doing the PhD in US, where he remained the rest of his life, the last 30 years. Now he is a professor in the Arizona University. His main field is the general relativity. He's an expert in general relativity, gravitation and general relativity. And within it, he was working in black holes and cosmology. In black holes, he was participating in the development of the idea of the EHT is the Event Horizon Telescope for the detection of the Event Horizon in the black holes. And in the last years, in the last decade, perhaps he was more involved in cosmology. He's one of the few persons, very fine specialists in general relativity, who is trying to give some challenging approaches to cosmology. And this is one of the examples of the talk that we will have here now. So the topic is about the inflation and some criticism, some doubts which can be given about the idea of inflation with the present now data. So please, you can start. Thank you.
Thank you very much, Martin. It's always a pleasure to be here, and I'm thankful that this is a third opportunity. I think everybody here knows that there is some growing tension between certain predictions of the standard model in cosmology and at least some of the data. But that's really only the tip of the iceberg, because those of us who are involved in trying to develop a comprehensive, self-consistent picture, a complete picture for how the universe started and how the universe is evolving, have to deal with much more serious problems than the small tension that perhaps everyone is aware of. As you'll see as we go forward, there are conceptual conflicts with the standard model that we have today. The model has been quite successful, there's no question about that, but there are still, after all these years, conceptual conflicts. These are serious physical conflicts that have not been resolved, and perhaps even worse, there are coincidences, some of which are completely unacceptable, and I'll show you one. This is what we have to deal with. In trying to construct a comprehensive theory, there's quite a lot that still needs to be done, and almost certainly there has to be some new physics developed. And we'll get a sense of this as we go through. We're not going to answer all the questions, of course, and there's a lot to say about this because there are many issues that we have to confront. So in an hour or 45 minutes, we're only going to have enough time to look at a sample of these issues, but what I'm hoping to do is to at least convince you that we're still very far from having a complete picture. So let's start by looking back to the beginning. Okay, we're going to look towards the singularity, the Big Bang, time t equals 0. And of course, general relativity is a classical theory, but as we look back towards the beginning, we can't avoid the question of how precise we can make measurements. Quantum mechanics, as far as we can tell, is correct. And quantum mechanics puts a limit on how with what precision we can measure distances as we get closer and closer to the beginning. It becomes a real barrier, a significant barrier. When we're talking about the earliest moments, we're presumably talking about the so-called space-time foam, which is sort of shown schematically here in this background slide. The space-time foam arises because of quantum fluctuations in the metric. And the size, the minimum size, is dictated by Planck's constant. We don't know where that constant comes from. But what we do know is that canonical quantization puts a limit on how accurately we can position a particle given its energy or momentum, and similarly for time. So let me just take a couple of minutes to explain what this is, because people always discuss the Planck scale and so on, but it's actually very simple to understand what that is and where it comes from. So the so-called Compton wavelength is the wavelength that a photon would have if it had the same energy as the particle that we're trying to observe. You know that in quantum mechanics, in order for us to understand where the particle is or what its properties are, we have to interact with it. We have to shine light on it. We have a choice. We can pick a photon that has a very low energy and a very large wavelength, and then we shine that photon on the particle. Because it has low energy, it doesn't create a lot of recoil, but the problem is that its wavelength is very large. On the other hand, if we pick a photon with very high energy, it has a short wavelength, gives us better precision, but in colliding with the particle, it creates a lot of recoil. Either way, we lose precision in determining where the particle is. So in quantum mechanics, the ideal situation is where the photon energy is the same as the particle's energy. And the wavelength that that photon has is then given by the equality of the photon's energy to the particle energy, which is what we call the Compton wavelength. Okay, it's very simple to understand. According to quantum mechanics, this is the smallest scale about which the physics that we have today can tell us anything with confidence. If we try to measure something smaller than the Compton wavelength, we have no idea how to do that, because Planck's constant is finite, and it doesn't get any smaller than it is. Presumably it was the same back then as it is today. So then, what else can we do? We don't have a theory of quantum gravity, but we have to use general relativity together with quantum mechanics. So what we do is we marry the two by finding the characteristic scale in general relativity that we can set equal to the Compton wavelength. So the way that this is done is, for the mass that's used to calculate the Compton wavelength, we determine its Schwarzschild radius, and then we simply set those two length scales together. This is the level. It doesn't get any more sophisticated than this, because we don't have a theory of quantum gravity. Well, this is all we can do. People sit at their desks, they get an envelope, back of the envelope calculation, and this is the way it's done, right? We set the Compton wavelength equal to the Schwarzschild radius, and then from that equality we get a unique value for the mass, the Planck mass, which is 5 by 10 to the minus 8 kilograms. And you notice that this is not really the mass of a fundamental particle. Electrons and protons are much smaller than that. So the Planck mass is not meant to be the mass of a fundamental particle. It's a characteristic mass for which the Compton wavelength is equal to the Schwarzschild radius. And then the other thing that we can do once we have this characteristic mass is to put it back into the expression for the wavelength and determine what physically the smallest wavelength is. And with that mass, this becomes the Planck scale. The Planck length is the Compton wavelength for the Planck mass, and it has a value of 10 to the minus 33 meters, which, as you can see, is much smaller than the size of a typical particle, because the mass is not the mass of the particle. And then we can make an additional assumption that the speed of light was the same back then as it is today, and we can determine the time that it takes for light to cover a Planck length. And so if we divide this Planck scale by c, we get the Planck time, which is 10 to the minus 43 seconds. So according to the physics that we have today, these are the scales that put a limit on how precisely we can make measurements. We cannot say anything about time shorter than 10 to the minus 43 seconds, and we cannot talk about scales smaller than 10 to the minus 33 meters. These characteristics are about as sophisticated as we can get. Someday when we have a theory of quantum gravity, maybe we can do away with this, and the theory will tell us something better, perhaps more accurately or with better justification. But most of what we know about the early universe is based on this foundation. So keep this in mind, because we'll be talking about certain issues involving inflation that are critically dependent on these numbers. So if these numbers are wrong for some reason, then the foundation for inflation is also in jeopardy. There are conceptual problems anyway, and we'll get to at least one of those shortly. So the other key thing, of course, is that you notice how important the Schwarzschild radius was from the beginning. When we talk about the Planck time or the Planck scale, that's all based on the reality of a Schwarzschild radius in a cosmological context. And yet, after the Planck time, we tend to forget about the role of the Schwarzschild radius in the cosmos. You don't hear of people talking about a gravitational radius in cosmology, but that apparently is wrong too, because the data today are telling us that we should be considering the Schwarzschild radius not only at the Planck time, but after that, because it was real then, apparently, so it would be real throughout the history of the universe, and it has something to do with how we interpret the data. So we'll come back to this a little bit later. Okay, so then after the Planck time, we assume that classical physics is okay, and we use one of the most famous, one of the simplest solutions to Einstein's equations as a backbone for the metric that describes the evolution of the universe. I think you all know about the Friedman-Robinson-Walker metric. It has a very simple form because it's based on this high degree of symmetry and simplification. We assume that the universe is homogeneous and isotropic, which leads to this extremely simple metric where there's only one function that's unknown throughout it. You notice that G00 is set equal to 1, for example. So already from the beginning, we don't even allow for time dilation to be present. All we're saying is that there's one function, this universal function, an expansion as a function of time, that tells us how any distance changes with time universally, no matter where you are in the universe. All these distances change in proportion, given that there's only this one function. So now, here is another problem, right? The standard model of cosmology is based on the Friedman-Robinson-Walker metric, which is a justifiable solution to Einstein's equations. But the problem is that knowing the solution to Einstein's equations doesn't tell us what the constituents in the universe are. So the standard model of cosmology today is still mostly an empirical theory. Even though it's based on FRW, we have to put in by hand what the various constituents are. And depending on their equation of state, we can change the way that the universe evolves, regardless of whether or not FRW is a valid solution. It is a valid solution, but knowing the solution doesn't tell us the rate at which the universe expands. To get that, we have to put in the density. We have to introduce radiation, we have to introduce matter, and apparently today there's at least one other component that we call dark energy. There are probably several, to be honest with you, but there's at least one other one whose equation of state we don't know. We have to guess all these things. And as a result of that, the standard model is very flexible because there are as many as 10 or 12 free parameters that we just don't have any idea about. For most applications, we end up having about 5 of them, like the equation of state of dark energy, the Hubble constant, the density of matter, the density of dark energy, and the baryonic density. And sometimes you can even do with fewer than 5. You can have maybe 2 or 3. So with this context, we can then summarize what the standard model predicts for the evolution of the universe, starting from time t equals 0 to today. So let me take a few minutes to describe what we're seeing here, because then with this plot, with this framework, I will also indicate to you one of the most serious conceptual inconsistencies, and also one of the most amazing coincidences that begs for a physical explanation. But before we get to that, let me just describe what we're looking at here. So first of all, this is the size of the universe on the vertical axis versus the time in seconds. And you can see the Planck time, 10 to the minus 43, where the space-time foam was located. And the size of the universe at this point, if you remember, was that 10 to the minus 20 times the size of a proton. So after the Planck time, following FRW, we would derive an expansion given by one of these red curves here. This is the classical cosmological model without inflation, which produced a significant inconsistency, a problem known as the horizon problem. The horizon problem, quickly described, is simply that when we look at opposite sides of the sky, we see the same temperature in the CMB, the cosmic microwave background. But if the CMB was produced at 380,000 years, as the standard model predicts, the universe would not have had enough time to expand to those positions in order to emit the CMB that we see today. That's the horizon problem. So to get around this, the idea of inflation was introduced about 37, 38 years ago. And what inflation does is to very rapidly expand the universe by many orders of magnitude between 10 to the minus 37 seconds and 10 to the minus 35 seconds. There are reasons from particle physics to suppose that a scalar field might have been present at that time, and the scalar field had to have just the right potential in order for the pressure in the inflaton field, as it's called, to be the negative of the energy density of the field. So in other words, as the universe expands, the negative pressure keeps putting energy back into the medium so that the energy density stays more or less constant, which leads to this very rapid exponential expansion. It's a de Sitter expansion, de Sitter space. So this is all meant to have happened before 10 to the minus 35 seconds, after which, in ways that we still don't understand, the inflaton field is supposed to have decayed and turned into particles that we know today, quarks, leptons. All of these were supposed to have been produced after this rapid expansion ended. But as you know, we don't have a particle physics model that describes that, because the inflaton field doesn't exist in the standard model of particle physics. So we suppose all these things to have happened, but we don't know whether they could have happened or not, because we just don't have a physical picture for how that could have happened. And the universe is supposed to have then been reheated, and it progressed through its normal expansion following the prescription from radiation, and then matter domination, and then dark energy. So this is the picture that we have today. And already you can see that there are some assumptions that need to be made that are not justified by the physics that we have today. It doesn't mean that they're wrong, but it means that there's new physics that we have to develop before we can be sure that this is even correct. But now let me show you a conceptual problem that is present even with the physics that we know today. So experts in inflation are actually more excited about inflation for a reason other than solving the horizon problem. That was the reason that inflation was invented. But inflation also apparently provides an explanation for how large-scale structure came to be, because the inflaton field would have had quantum fluctuations which grew and became the seeds for the formation of galaxies and clusters. It's a very beautiful, elegant picture if it's right. But here's the inconsistency. In order for these fluctuations to have grown and to have the correct properties, they would have had to have started forming way before the Planck time. There are at least two reasons for that. One is that in order to use canonical quantization, as we understand it, we have to have the seeds form before the space-time curvature becomes important. That means that the wavelength of the fluctuations had to be much smaller than the Schwarzschild radius when they were born. So that has to happen way before the Planck time, when they were very tiny. The second reason is that in order for them to grow in amplitude and become large enough to make the seeds for galaxies and clusters, there had to be enough time for them to grow to that point, which means that they couldn't have started at the Planck time. They had to start orders of magnitude before that. If you're aware of conformal time, the way that this is described is that this would have essentially had to happen almost in the infinite conformal past. I know that 10 to the minus 43 seconds is a small time, but imagine cutting that, and getting closer and closer to zero. So why is that a problem? Well, think about this, right? We're using quantum mechanics to argue that the inflaton field had fluctuations. But then we're saying that in quantum mechanics, the Compton wavelength is the minimum scale that we can have any confidence in saying anything about with the physics that we know today. And yet we need these fluctuations to have started orders of magnitude below that scale. How do we describe these fluctuations when in quantum mechanics we have no way to do that below the Compton wavelength? So the experts who work with this are aware of this problem. And what they talk about is eventually developing what they call trans-Planckian physics to be able to deal with this. But the bottom line is we don't have the physics today. Okay, so when people talk to you about the inflaton field and quantum fluctuations creating large-scale structure, you have to keep at the back of your mind that this is all based on an inconsistency with quantum mechanics. We use quantum mechanics to create the fluctuations, and then we ignore the fact that this violates quantum mechanics. So, you know, eventually maybe we will have the physics to do this properly with trans-Planckian processes, as I say. But as of today, we don't know how that can happen. Okay? So inflation is a wonderful idea, but it's not a theory. It's very incomplete. Now that let me mention to you an example of a coincidence which is extremely hard to accept. So you notice that there's a very complicated evolution in the size of the universe. There's inflation, there's deceleration, then there's acceleration, and so on. But the size of the universe today, at 10 to the 17 seconds, is exactly the same as it would have been if the universe had simply been expanding at a constant rate. Really? You know, with all the possible flexibility that the universe could have had in expanding, you know, with various phases of deceleration and acceleration, it ends up being the same size today as if it had expanded at a constant rate all along. How does that happen? And the worst part of this is not only the coincidence, but it's the fact that this coincidence can only happen once in the entire history of the universe. And if the universe is open, then the timeline is infinite. So the probability of this happening today is essentially zero. We are so lucky that we're looking at the universe at just the right time when its size fits this coincidence, that it's exactly the same as it would have been if the universe were expanding at a constant rate. So these are two examples of why there is no question that the standard model of cosmology is at best incomplete, but there are serious problems that have to be overcome. So now let me just summarize a couple of additional ideas associated with this, and then we'll get to the data, because the primary focus of what we want to do here is not so much to go through the details of deriving these quantities. That's always easy to do, you know, when you have peace and quiet. But the most important thing is to see how the data are interpreted and what they tell us in the context of what we just said here. So this coincidence, by the way, means that if we average the total equation of state, the pressure of the cosmic fluid divided by the density over a Hubble time, it comes out to be -1/3. It's interesting because in general relativity, that's not a random number. That's known as the zero active mass condition. In general relativity, there are two kinds of masses. There's inertial mass that tells you how a particle responds to the curvature, and then there's the active mass that creates the curvature. So the curvature is due to more than just inertial mass. There are other sources, energy, you know, pressure, that create space-time curvature. So when you say zero active mass, what you're saying is that there's no source of curvature. So this is an important number because the data seem to be telling us that as the universe expands, there's actually no source of space-time curvature. There's obviously density, there's pressure, but the two seem to be combined in such a way, rho plus 3p equals 0, so that there's no net acceleration in the universe. Okay, so the simplest way to get around this strange coincidence is to suppose that this condition is true all the time. Not that it happens on average when we're looking just now, but that it's there all the time. This is just a simple idea. There's not very much physics justification for that because we don't know enough about the equation of state in the cosmic fluid. So this is a simple idea. Think of it as a toy model, that the universe might have this condition present all the time. When we look at the tension between the predictions of the standard model and some of the data, we will be also comparing with this simple toy model, just to give you an idea as a baseline of how big the tension is or what the tension might actually mean. And there is both an observational and a theoretical justification for why the universe might have this condition, although the justification admittedly is not very strong yet. So from an observational perspective, these are the equations that one gets when the Friedman-Robinson-Walker metric is folded through Einstein's equations and we solve for that function a of t. These are the equations for a of t. And again, the details are not so important, but I just want to show you formally where the zero active mass condition comes from. So this is the Friedman equation, which is actually an energy conservation equation. This is the kinetic energy of expansion, the negative gravitational potential energy, and K, the spatial curvature constant, actually has a physical meaning. It's the negative of the total energy in the system. So when we say that the universe is flat, K is 0, what that means is that the total energy in the universe is 0. The kinetic energy of expansion is balanced exactly by the negative potential energy, the gravitational potential energy, which, by the way, is a very elegant universe. That if you were creating a universe, that's how you would create it, with 0 total energy, so that it's always balanced exactly. If K were not 0, we would have to explain where that energy came from in the first place. That's a different issue, but it's a very beautiful, elegant universe to have K equals 0. But the equation that's relevant to this point is the acceleration equation, this one here, which is the equivalent of Newton's equation of motion for this expanding fluid. And you can see that the acceleration of expansion, A double dot, is proportional to rho plus 3p. This is the total active mass that I was referring to before. So if we suppose that the acceleration is 0 at any given time, then that means that rho plus 3p has to be equal to 0. That's where this constraint comes from. There's also a theoretical justification. Again, we won't spend more than a minute on this. I just want to give you a sense that there is a theoretical justification for it. If we start with a metric that does not force G00 to be equal to 1 before we fold it through Einstein's equations, and then find the equations of motion and solve for this lapse function, as it's called. G00 is also known as the lapse function in general relativity because it tells us how much time dilation occurs between the accelerated frame and a local inertial frame. So this lapse function depends, again, on rho plus 3p. So to make this function be 1, which is what we want for Friedman, Robinson, Walker, then we need rho plus 3p to be equal to 0. So it appears that the Friedman-Robinson-Walker metric is so special that it not only requires isotropy and homogeneity, but it actually also requires a 0 active mass to be valid, because we force G00 to be 1 from the beginning. So there are possible ways around this. This is not a complete justification, but there is some motivation for thinking that the universe selects 0 active mass, both for observational reasons in terms of our perspective and also theoretically. Okay, but now let's talk about the tension between the data and some of the predictions of the standard model, and then we'll focus on the CMB work that we completed here at this institute about a year ago now, almost. So let me show you a couple of examples of how to interpret the data and why there's a lot of flexibility. So we'll start with possibly the best known observations, which are the type 1a observations. As you know, this work led to the Nobel Prize a number of years ago because it confirmed the existence of dark energy and presumably also an acceleration phase that we see today. Type 1a supernovae, however, are not standard candles. They're not perfect. Type 1a supernovae occur when a white dwarf accretes and goes over its Chandrasekhar limit and collapses to a neutron star. So in principle, you can imagine that if the Chandrasekhar limit is perfect, then that always happens at the same energy and we create a standard candle. But unfortunately, the reality is that this process depends on the abundance in the white dwarf, the CNO abundance. It also, the way the supernova behaves depends on the environment. So these are not perfect standard candles. There's some scatter in the maximum light versus the rate of decay in the light curve. But one can very cleverly, as these supernova teams did, create a parameterization of the light curve to take all of these factors into account. And unfortunately, though, that means that you're introducing 3 or 4 nuisance parameters, as they're called, that describe the shape of the light curve. There's no way for us to determine those parameters without assuming a cosmological model. So the way that this is done is you assume a model, and then you simultaneously optimize the parameters of the model with the nuisance parameters. That means that the data are very compliant to the model. You can change models, you recalibrate the data, and you get a reasonable fit, even with different models. And I'll show you an example of that. So, first of all, here is how lambda CDM, the standard model, accounts for these type 1a supernovae with the distance modulus as a function of redshift. The reduced chi-squared is an incredible 0.999. Obviously, this is a remarkable fit, right? But now, let's see what happens if instead of just lambda CDM, we impose zero active mass. And then we do the recalibration, we get the same chi-squared, reduced chi-squared. But notice what's happened in the process. The curve has changed, but so have the data. The data have shifted slightly. So what this shows is that type 1a supernovae don't necessarily prove that the standard model is correct. What they show is that the standard model is consistent with type 1a data. But as you can see, there's at least one other model that can do just as well as lambda CDM. It's important to understand this because there's no tension between lambda CDM and the type 1a data, but there is tension with other kinds of data. And the question always comes up, but what about type 1a supernovae? Because they fit exactly. Yes, they fit exactly because of this freedom that we have to recalibrate the data for each model that's tried, and we don't know what the data are absolutely. We always have to assume a model first, and then we obtain the data, then we reduce the data. So you have to remember that the data are compliant to the model. And in fact, to be honest, when we compare models, if you do model selection, and I know that some of you already do this with other kinds of data, you know that because of the different number of degrees of freedom and the number of free parameters, it's not enough to compare the chi-squared. You have to use information criteria. And information criteria punish models that have higher numbers of free parameters. So in fact, when you compare these two models, because the zero active mass model has far fewer parameters than lambda CDM, it actually has a much higher likelihood of being correct according to type 1a data. So to be fair, they're not even just comparable. Lambda CDM is disfavored compared to models that have fewer parameters. But we don't need to dwell on that because there are other kinds of data that we can look at. So another comparison that can be done is something that I did with Martine here about a year and a half ago, applying the Alcock-Paczynski test to baryon acoustic oscillations. The way this works is that there were acoustic waves presumably generated right after the Big Bang, and these acoustic waves expanded at relativistic speeds because the baryons and the photons were coupled in the beginning until decoupling, until protons and electrons combined into hydrogen, and then the radiation was free, and so the speed with which the acoustic waves spread decreased significantly. What that did was to create fossilized features, the so-called acoustic scale, on an acoustic scale, which depends on how much time the waves had to propagate, which apparently was about 380,000 years in the standard model. But then as the universe expanded, these features kept growing with the overall expansion of the universe, and created features in the distribution of galaxies in clusters. Okay, these are the baryon acoustic oscillations. Now, what one can do is to identify a cluster of galaxies, say, that's more or less spherical, and then one can measure the size of this distribution, assuming it's spherical, using both the change in redshift. Imagine that we're looking at it from the bottom here. So we can measure the change in redshift from the back of the cluster to the front of the cluster, which gives us the diameter S parallel along the line of sight. And then we can also measure the diameter using the angular separation from one side to the other, and take the ratio of those. If space is Euclidean, if the universe has zero space-time curvature, then this ratio should always be equal to 1 for a spherical distribution. Of course, the universe does not have zero space-time curvature, and so when we measure this ratio, we get values that differ from 1, and the difference increases with the redshift. These are the three most accurately determined values of YZ, as you can see at a redshift of about 0.37, 0.54, and 2.34. What's significant about these data is that the errors are very small. They're about 4% errors, which actually are even better than the errors associated with type 1a supernovae, which have an intrinsic error of about 5%, and it looks like that's always going to be the limit with those sources. Anyway, this is what the standard model as we have today, this is how it fits these data. As you can see, it fits fairly well at low redshift, but then it misses the other 2 points. And in fact, the highest redshift point, it misses by more than 2 sigma. When the overall analysis is done with all 3 data points together, the disparity, the tension, is approximately 2.5 sigma, which is not overwhelming, but it's not something that can be ignored. If this was a slam dunk, as they say, then this should have done much better with these 3 data. And in fact, by comparison, this is what the zero active mass condition, remember this toy model, this is how it fits the data. It goes right through the data points. And this curve doesn't have any free parameters. It's an absolute curve. It either fits the data or it doesn't. So you can see the level of tension associated with the BAO. As I say, it's not overwhelming, but 2.5 sigma is not something that can be ignored. And then finally, let me show you a different kind of tension before we get to the CMB, the angular correlation in the CMB. This is a famous diagram. I'm sure you've seen it many times. It's a very beautiful diagram because it shows the different epochs quite well. What I want to emphasize is that between recombination at about 380,000 years and the first emergence of population 3 stars about 400 million years later, there were no objects in this region producing light. These are the so-called dark ages. And then from 400 million years, we had the evolution of population 3 to population 2, population 1 eventually today, and quasars presumably started forming with population 3 supernovae, which created the seeds. So notice that with this simple-minded diagram, which however is consistent with all the constraints that we have in the standard model, quasars would not have started growing until about 400 million years after the Big Bang, because that's when the first stars would have generated the seeds. But this creates a problem now, because we see supermassive black holes at a redshift of 6 and 7 in a few cases. In the standard model, that corresponds to an age of about 800 to 900 million years after the Big Bang. So if we try to grow these quasars by standard astrophysics using Eddington limited accretion, we find that they would have had to start growing before the Big Bang in order for them to get to the mass that we measure at a redshift of 6 to 7. The way that people try to get around this is to suppose that either there was some alternative exotic mechanism for making 10 to the 5 solar mass seeds at about 400 million years, right? We don't know what that process is. We see no evidence of this anywhere in the universe, either locally or at high redshift. But this is what would be needed in order to make these objects grow to their observed mass in only 500 million years. The alternative to that, and this is something that the Cambridge group introduced with Martin Rees and his group, was to suppose that the accretion is greatly super Eddington. And of course you can make them grow in 500 million years if you have greatly super Eddington accretion rates. But again, we have no evidence of this anywhere. We don't see super Eddington accretion here, we don't see it at middle redshifts, we don't see it at high redshifts. So we have to invoke something quite different from ordinary astrophysical processes that we're familiar with, and we would need to hide them somehow in order to make it work. So this is the tension with the timeline in the standard model. The standard model seems to compress the time too much at the beginning of the universe. And again, just for comparison, if you assume zero active mass, this is how the growth of black holes would have looked. In the early universe, the time is stretched by about a factor of 2. We end up with the same age of the universe today, but the universe was stretched. The timeline was stretched at the beginning and then compressed a little bit later on. So as far as the black holes are concerned, though, normal Eddington limited accretion would have allowed them to grow from 5 to 20 solar mass seeds after the dark ages ended, when stars started forming, and become these 10 to the 9, 10 to the 10 solar mass objects by redshift 6 or 7. So again, this is not a proof, right? But when you start to look at all the different pieces of the puzzle, and all of them seem to fall on one side and not the other, you have to start questioning whether we're missing something significant in the standard model that we have. Okay, so these are the kinds of things that create the tension. But now let's spend the remaining 20 minutes or so about the main point of this discussion, which is this wonderful new result that we have with Ricardo and Martin that we developed about a year ago on my last visit last summer, which has to do with this improved analysis of the angular correlation function of the CMB. Now, as you know, there have been 3 satellite missions, at least 3, that have made significant observations of the CMB, starting with COBE in the 1990s, and then WMAP, and culminating with Planck. By far, Planck has the highest precision with these measurements, and so we're going to see results that are only possible by analyzing Planck data. There were hints of this before, both with COBE and then with WMAP, but it's really the Planck analysis that makes all of this happen, as you'll see. So the idea is, let me again spend a few minutes giving some background. What we do is we assume that the temperature in the plane of the sky is a Gaussian random field. That means that we can then describe the temperature as a superposition using spherical harmonics. So when people talk about multiple components in the CMB, these are the multiple components defined in terms of the spherical harmonics. There are different ways of defining multiple moments, of course, but these multiple components are specifically in terms of the spherical harmonics. These ALMs are the expansion coefficients, both in terms of poloidal angle theta and azimuthal angle phi. And as you know, what matters is not the orientation of the vector between 2 points, just the angle between them. So the azimuthal orientation is irrelevant. And that's why it makes sense to sum over all the azimuthal components m and to form this coefficient CL, which is referred to as the angular power of multiple L. So this angular power corresponds to a multiple that's associated with the poloidal angle theta. We've summed over all the azimuthal components, okay? So this is, when you see these beautiful plots of the angular power spectrum that I'll magnify on the next slide from the CMB, what we're looking at is the size of CL as a function of L. These are the angular power for each of the multiple components L, in principle from 2 to infinity if we had enough data, but typically from 2 to about 2,500. Okay, so this is the angular power spectrum, which we're all familiar with, but for reasons that we'll get into shortly, this is actually a very limited way of analyzing these data, because as you'll see, it amplifies the information between 1 degree and 0 degrees. The sky is 180 degrees, but most of the information that we get from this angular power spectrum is limited to these tiny degrees. So this is where the angular correlation function comes in. The angular correlation function uses the same data. There's nothing different except that it displays the data in a different way. Instead of emphasizing the angles between 1 degree and 0, it emphasizes the angles between 1 degree and 180 degrees. The angular correlation function is the average of fluctuations in temperature in 2 different directions. So that means that you get it as a function of angle. If there was no correlation in the fluctuations at these large angles, the average would be 0, right? So the angular correlation function, if it's not 0, it means that there's some physical connection between the fluctuations that you see in different directions. And that physical connection, in principle, depends on angle. So it's described in terms of this sum this expansion, in terms of Legendre polynomials and these coefficients, which again are the angular power of the multiples L. And by the way, when you see this display, you're not really seeing CL, because CL depends very strongly on L. So if you go from L of 2 to 2,500, this 1 over 2L kills the value of the coefficient. It makes it hard to display these things. So what you really see is this reparameterized DL, which is simply CL, but with a renormalization out the front. It just makes it easier to plot these quantities. Okay, so now let's look at this beautiful angular power spectrum. This is easily one of the most spectacular successes of the standard model. No question. You know, the standard model fits these peaks beautifully with high precision. But we need to look at this more carefully and understand the physics behind it. What we're looking at, as I say, are features below 1 degree. And these are features that, as we understand, were created by the propagation of acoustic waves in the early universe. In fact, the first peak corresponds to the size of the fossilized region created by the first acoustic wave, which then ended at recombination. And this all fits very nicely within the picture, and the subsequent peaks then have to do with other acoustic features. But notice that what we're talking about is local physics. We're talking about the physics of waves propagating through the medium. So this depends on the density of the medium, the baryon concentration, the speed of sound in the medium. It doesn't depend on the dynamics of expansion. And in fact, it's been known since the 1990s that you can fit a spectrum like this with many different varieties of lambda CDM, many variants of lambda CDM. In other words, this angular power spectrum does not distinguish very well between different cosmologies, because it doesn't depend on the dynamics of expansion. It depends on the local physics of wave propagation through the medium. Instead, in order to distinguish between cosmologies, we need to look at large angle phenomena in this region here. And you can already see that the situation is quite different here. It's quite messy. It's not as beautiful as what you see on small angles. So let's look at these two separate domains. So at small angles, we're looking at the propagation of waves during the first 380,000 years or so. And this little simulation shows you how these features arise. You get these spherical regions created by acoustic waves, which then get superimposed, and we see the overall fluctuation distribution from which we get this power spectrum. But we're talking about small-scale features. These are not features that are associated with the overall expansion of the medium. Okay? On the other hand, when we look at angles that are bigger than 1 degree, what we're looking at is features created by an entirely different process. It's a process called the Sachs-Wolf effect. This effect has to do with perturbations in the metric created by density fluctuations, not waves, not acoustic waves, but density fluctuations that grow, and these create fluctuations in the space-time metric. These are the sources of the fluctuations on large scales. And this diagram, created by ESA, demonstrates why there's a problem on large scales. This is the map created by Planck, and then if we subtract from this a map predicted by the standard model, we find that there's a residue. And the residue between them is mostly on large scales. You don't see tiny fluctuations appearing on this difference. You see the large scale fluctuations. So what this is showing is that even though the small scale fluctuations are consistent, the large angle fluctuations are definitely not. And in fact, the disparity is huge. It's not even a small tension, it's a very large tension. So let me just take a couple of minutes to demonstrate how this analysis is done. We don't have to go into all the derivational details again, but what one can do is to use the fact that the small scale fluctuations are physically separate from the large scale fluctuations and write the coefficients for L less than about 30, which corresponds to the large angles, just in terms of the Sachs-Wolf effect. Of course, the way that this is done formally is using all the physical effects together. But if we know that the fluctuations on large scales are created just by the Sachs-Wolf effect, then one can restrict the integral to just this form, which is a lot easier to deal with. Again, the details are not so important, but I want to show you what's involved in calculating these coefficients. One extracts from the data the power spectrum of the fluctuations, which, as is well known, appears to be a power law that's almost that has almost a linear function of k. N is not exactly 1; it's about 0.96, but it's a power law, and it's almost a linear dependence on the wave number. And then with this power law, one can calculate the contribution to the large-scale features that arise from these metric fluctuations. And it turns out to be an integral over the spherical Bessel function. The argument, by the way, is fairly interesting. It's essentially the ratio of the co-moving distance between us and the surface of last scattering divided by the wavelength associated with this wave number. The wave number is 2 pi over lambda, of course. So what we'll be looking at next is the dependence of these large-scale fluctuations on the minimum of the wave number. This may not seem like a big deal, but in terms of inflation, it's huge. Until Planck, this always had to be set equal to 0, and the upper limit is infinity, because the data were not precise enough for us to test one of the most important requirements of inflation, that there be no length scale associated with the fluctuations as they cross the horizon and then come back. But now with Planck, we can test whether this is actually 0 or not. If this is not 0, then there's a significant problem with the standard inflationary picture. So this is what we're going to do. We're going to examine whether the data can distinguish between values of k-min of 0 or not. And because k-min can vary over huge factors from very small numbers to very large numbers, what we do is we renormalize it by simply multiplying by this co-moving distance so that we get a dimensionless number u-min, which is, remember, proportional to k-min, but it's of order 1. So you're going to see u-min that goes from 0 to 3 or 4, or something like that, whereas k-min would vary by orders of magnitude. Okay, so now let's get to the results. This is the beautiful diagram that was produced here, principally by Ricardo and Martin, and this shows the measured angular correlation function as a function of angle from 0 to 180 degrees. If you know anything about this from previous missions like WMAP, you'll be amazed at how small these errors are. These are the 1 sigma error bars corresponding to the measured angular correlation function, which is shown in black. WMAP didn't even come close to this. But here is the issue, right? It's been known since COBE, about 25 years ago, that there's a deficit of angular correlation at large angles. You notice that the angular correlation is not 0 everywhere up until about 60, 70 degrees, and then it appears to go to 0, which is anti-inflationary. Inflation predicts angular correlation at all angles. So already there was an issue 20 years ago. And since then, there have been attempts to try and mitigate this result, discussing the possibility of not doing the foreground subtraction properly, or there being other reasons why it would appear that the angular correlation goes to 0 at large angles. But with Planck, I think most of those possibilities, maybe all of them, can now be done away with because the errors are so small. This is what the standard model with slow roll inflation predicts. It misses everything. In the old days, with WMAP, it was not possible to see this because the errors were bigger, and it looked like the angular correlation at least was consistent with the measured one at small angles, and then this disparity here is what was explained away by having some background issues, some improper subtraction of dust contribution and so forth. But you can see now that this is quite serious. This is not something that can be brushed under the carpet very easily. You can notice that the predicted angular correlation misses the minimum It misses the value there. It misses the fact that there's very little angular correlation at large angles, and actually it's 2 sigma different even at small angles. So basically it's wrong everywhere. Instead, this is what we need to do to fix it, and this is the work that we did here last summer. We can vary U min or K min and optimize its value until we get a good fit. This is the best fit that was possible to achieve with a value of 4.34, which basically gives us essentially the number of wavelengths between us and the surface of last scattering. And you can see that this curve is consistent with the measured value within 1 sigma everywhere, even here at the minimum, the location of the minimum. And what we see is that the angular correlation is not exactly 0, it's small, but it's fit much better with a non-zero value of U min. So what does this mean? Well, it means that with this optimized value of U min, we know that with the correct error handling, the value is not 0, it's 4.34 plus or minus 0.5. That's important because what it says then is that the value of 0 is ruled out at over 8 sigma. Slow roll inflation requires a U min of 0. The fact that this rules out a U min of 0 at 8 sigma means that the conventional model of inflation as we have it today is ruled out at a very high significance level. This is hard to believe, I know, especially for people who work with inflationary cosmology as it's stated today. But the data are the data. I don't know how one can get around this. The only way to fix this is to be creative and modify inflation in such a way that it ends up having a length scale. I don't know how to do that. But, you know, people who work with inflation are very clever, and over the years they've kept adjusting it and, you know, making it fit the data as we go. And perhaps there's a way around this. Maybe there is a way to introduce a length scale, but slow roll inflation does not have a length scale. And here's what's even more intriguing. What's more intriguing is that the value of U min, the value of this minimum wave number, is not random. It corresponds to a wavelength which is equal to the Hubble radius, which is the gravitational radius at decoupling. So here we come back to something that we suspected in the beginning when we talked about the Planck scale, the fact that we had to introduce the gravitational radius at that point, and then it's usually ignored, but suddenly it reemerges here, because when we analyze the CMB data, we find that the gravitational radius apparently has something to do with the power spectrum that we see in the fluctuations. This number is not random. It's equal to the gravitational radius at the time of decoupling. So the Schwarzschild radius is something that apparently is significant in determining how the universe evolves all along, not just at the beginning, at the Planck time. So these are the two principal conclusions that we have from this work, that slow roll inflation is ruled out at a very high level of significance, and also that the gravitational radius apparently is important even after the Planck time. Now, as one last thought, and this will only take a few minutes, the question is, can we survive without inflation if it turns out that inflation is wrong? The answer is absolutely yes. In fact, it's more difficult to think of inflation fitting in the scheme than not fitting it in the scheme. So the horizon problem, to be clear, in the standard model, the horizon problem arises because the universe decelerated at the beginning. It didn't have enough time to expand to the position where it needs to be to create the CMB that we see today. Had the CMB been produced at 2.4 gigayears instead of 380,000 years, there would be no horizon problem. So it's not an absolute problem, it's a relative problem. It has to do with how much the universe expanded in the beginning. It turns out that if the universe expanded at a constant rate in the beginning, there's no horizon problem. And I'll show you this graphically. The point is that when we look at two patches of the sky on opposite to us, so we're B in this picture, and we're looking at two diametrically opposite patches, shortly after the universe starts to expand at 0, patch A can send a signal to patch C, And because this is traveling at the speed of light, it will always get there at some point. But the time that it takes to get there depends on how rapidly the universe expands. So, again, we won't go through all the details, but this is the graphical result of this kind of analysis. RAC is the proper distance between the two patches. RBC is the proper distance between us and one of the patches. We're looking at the light reaching us along these null geodesics. This is the distance, the proper distance as a function of time. The black curves are the curves followed by light along these null geodesics, and we see the light at time t0 today. In order for us to see the light coming from opposite sides of the CMB, we need this distance here to be the same as the distance from here to 0. In other words, if we're looking at opposite sides of the sky that are in equilibrium, the light is coming from diametrically opposite patches that have twice the proper distance as the distance between us and one of those patches. So in other words, just to keep it as simple as possible, the distance between delta and eta has to be the same as the distance between 0 and delta. The reason that it doesn't work in the standard model is because there's deceleration, which you can see because of these curved trajectories. However, if we have a constant expansion rate, this distance is always equal to the lower one. And it doesn't matter when the emission occurred, because there's a fixed ratio with this constant expansion, opposite sides of the sky are always in thermal equilibrium. It's amazing, really, how this works. It's only because the universe decelerates that we have a horizon problem. If it expanded at a constant rate, or faster even, for which there's no evidence, but if it expanded at a constant rate or faster, there's never a horizon problem. So the bottom line is that because of all these difficulties of making inflation fit with the data, and because it looks like the data are telling us that there's zero active mass anyway, perhaps the simple answer is that there was no inflation, because we don't need it if the universe expanded at a constant rate. It's all very simple. It's always in equilibrium, and it explains the quasars in the early universe. It explains the baryon acoustic oscillations. It does everything much more simply. But in order to make this work, then there has to be new physics, because we don't know why the constituents in the cosmic fluid would maintain that special equation of state. So either way, whichever way we look at it, there's a lot missing, and we're pretty far from having a self-consistent picture. There's no question about that. Okay, I'll end there, and I'll be happy to answer any questions if anybody has any. So, Helmut?
Fulvio, thank you very much for this very interesting talks. Questions to CMB?
Well, this is on the horizon problem itself, because when we state that there is the cosmological principle that says that the universe is the same everywhere and the physics is the same, I don't see the reason for having a problem with the horizon, because the universe was started with the same physics, so the temperature of every place is going to be the same, even if they were or not connected.
Right, so
that makes sense, or not?
It does, yeah. But what's usually ignored when people talk about the cosmological principle is that we are not causally connected to the whole universe. The universe apparently is infinite if it's open. We are only causally connected up to a maximum distance that's dictated by the gravitational radius. You notice that even at the Planck time, we said that the only mass that we can use is the mass within the Schwarzschild radius. The argument for that is that that's the causally connected region at that time. So the only thing that we can say for sure is that the temperature should be the same everywhere within the gravitational radius, or up to the Hubble radius, but not beyond. There's no physical justification for us to say that the temperature has to be the same within the Hubble radius as it is outside, because in principle there's no causal connection between these two regions. So the cosmological principle, yes, it's meant to apply everywhere, but one has to add the additional condition that there's a causal restriction on how far we can apply that. We can't say that the universe started out being in perfect thermal equilibrium, because we don't know why that would happen. This is what they used to call a special initial condition to make that happen. So before inflation, the way people explained this away, they said, is there some special initial condition that makes the universe be in thermal equilibrium everywhere? But that's not physics, that's just a statement. It's a good question because, you know, often we hear about the cosmological principle, but it's not enough. Actually, we also need Weil's postulate, which tells us that the cosmological principle applies from one time to the next, because the cosmological principle in principle is only valid at one instant of time. But to guarantee that it stays for all time, we have to also introduce Weil's postulate. So it's not enough by itself.
At the beginning, in one of your first slides, you mentioned that there was an extraordinary coincidence about the expansion of the universe at a constant ratio to reach the actual size of the universe.
Right.
Which is the ratio that you have used for this calculation? Because, of course, the slope, at present there is some size of the universe and you can fit the slope to have this coincidence. But I suppose you are mentioned that this slope is predetermined in some way. Okay.
Yes, so that's based on the equality of the age in both situations. So if you calculate the age using the standard model with the initial deceleration and then following the acceleration, you get about 13.6 billion years. And during that time, if the universe were expanding at a constant rate, essentially the speed of light c, you get the same age for the same size. So in other words, it's the age that determines it. The size of the universe is based on that age times the speed of light c. But yet in the standard model, the expansion was not always c. It was sometimes slower than c, and there was curvature, there was acceleration now and deceleration. So it's actually based mostly on the age calculation in the two scenarios. The age comes out to be the same.
Further questions?
I have several questions, but I was most interested in the one of the last sentences that you were mentioning about what is your proposal for the possible constituents of the universe in the case of zero active mass, because anything that we know, normal matter, radiation, anything is changing with time. And if you are proposing something that is going like ρ plus 3p equals 0 all the time, it's something that has to be even true today. So that means that we are not dominated by matter or dark energy. We are dominated during the whole history of the universe by a new species,
Right.
which is having these strange properties.
Right. Very good point. So here's the point. We know that there's matter and we know that there's radiation, and there's very good evidence, regardless of which cosmology we use, that there's at least one other component, dark energy, whatever that is, right? So the principal question is whether dark energy is a cosmological constant or not. As you know, there are already other models, quintessence models, in which dark energy is dynamical. It's not a cosmological constant. So the zero active mass condition would be one special case of a quintessence model, but it requires that dark energy evolve as a function of time in just the right way to always guarantee that ρ plus 3p is equal to 0. So it's not a typical quintessence model, but it's a little bit like that.
But if you extrapolate that back
Yes.
to the beginning,
Yes.
is that making, I mean, a weird value of the total density?
So just to
of
give
energy?
you're asking exactly the focus question, which is at the heart of all of this, to make it work. So if the equation of state of dark energy were, say, minus 1/2, which is not unreasonable, but if it were minus 1/2, it means that the cosmic fluid at early times would be composed, as it turns out, when you do the calculations, it would be composed of 20% of radiation and 80% of dark energy, and that gives you ρ plus 3p equals 0. And then there was a transition to today where we have 30% matter, which includes matter and dark matter, baryonic matter and dark matter, and 70% dark energy, and that again gives you ρ plus 3p equals is equal to 0. So it's in this simple toy model, which is not a physical justification.
So it's not an exact equality, but it's something that is approximately keeping zero acceleration.
So in other words, you can always pick the dark energy equation of state to make it work. It doesn't prove that that's right, right? But there is a way to do it, because if there were no way to do it, then you'd have to worry about whether this is even realistic. But as I say, you can have 20% radiation, 80% dark energy, which turns into 30% matter, 70% dark energy today. And very interestingly, when we look at the abundances today, we get about 30% matter and 70% dark energy anyway, which is not so ridiculous, you know. But that's by no means a physical model. But let me also say that if this is going to work, and remember it's a toy model, right? It's not complete. But if this is going to work, what would justify that equation of state is not the properties of the fluid, but the properties that come from general relativity. So it's really driven by GR, which forces the constituents to behave that way. The analogy that might be a good one here is if you have a piston and you put certain chemicals, certain elements inside the piston, you can control the chemistry by adjusting the piston. You can decrease the pressure, increase the pressure, and you force the equilibrium to always go in the direction where you balance the pressure inside and outside. So this would work a little bit like that, in the sense that GR is dictating what the pressure should be, and then the elements have to adjust themselves. Obviously, dark energy would have to be dynamic. It has to be a particle of some kind. And then physics beyond the standard model would tell us what those interactions have to be in order to maintain this equation of state. But absolutely, there's no physical model for this, right? So let's not jump ahead. But this is just a plausibility argument for why or how that could come about.
Well, several comments. Inflation, I thought, was originated as an idea to get rid of topological defects and not to solve the horizon problem. Isn't that true?
The horizon problem was the first, and then the topological defects came second, and then there was that other argument that was made about how you can maintain flatness in the universe. It has a simple explanation for flatness. The topological defects depend on grand unified theories. We don't have a complete understanding of that. But the flatness argument is a little spurious because, as I say, when we talk about spatial flatness, what we really mean is that the total energy in the universe is zero. So if you were God and you were creating the universe, what value would you pick for the energy? Would you pick zero, or would you pick a positive energy or a negative energy? And then why? You know, why would it have a particular value? Zero is the most elegant, aesthetically pleasing value for the energy. So when people talk about spatial flatness, they don't phrase it in that terminology, but that's what it is. Spatial flatness means that the energy is zero. So the kinetic energy of expansion is exactly balanced by the negative energy, the gravitational energy. And you know, people who like this idea of a quantum fluctuation starting the Big Bang, that's what they would need, because the quantum fluctuation would have happened in vacuum with zero energy to begin with, and so you have this fluctuation which separates positive and negative energy, and then the evolution of the universe is simply restoring that balance. So our distant future is where the kinetic energy goes to zero and the potential energy goes to zero, and we recover the vacuum condition that the universe had before the Big Bang. Who knows if that's right, but that's the kind of aesthetically pleasing picture that one has with k equals zero. So inflation is necessary to force k to be zero only if k starts out not being zero at the beginning. But if it's zero at the beginning, it would always be zero anyway. So you don't need inflation to do that. But the main thing, and I still remember the day that Alan Guth came, I was a student at MIT at the time. You know, we heard his introductory talk on this. The very first thing he said is, I have a solution for the horizon problem. So that's how he introduced it. That was the reason for introducing inflation.
Okay, I thought in his paper he was focusing more on this magnetic monopoles and stuff.
There was a second paper that he wrote with his graduate student. I think that came a few months later, but the very first one had to do with the horizon problem.
I have a question regarding your BO Paczynski test, because there's an uncertainty due to the redshift space distortions, you know.
Right.
And that makes the...
This is the excellent work done by my friend Martin. So you know that there are about 30 measurements, BAO measurements, right? I only showed 3. The errors with most of those measurements are very large. They're like 20 or 30%. And one of the reasons the errors are so big is because it's difficult to disentangle RSDs from the actual effect that you need to measure the baryon acoustic oscillation. There's a degeneracy in the redshift measurements. These three measurements are very special because the BAO feature is thin and very high signal to noise. So the RSDs will affect the width of the peak, but they don't affect the position of the peak. So you can measure the BAO very accurately, even if there are RSDs present. That's why these three are so special. The errors for these three measurements are 4%. The others are like 20, 30%, and it's difficult to use those to do model selection. So that's why I only showed these three. They're very special compared to the others.
Yes, but to do the Alcock-Paczynski test, you need to take into account perpendicular and parallel.
Right. But you get one feature which then you can use. In this, the BAO feature stands out very cleanly from the RSDs. This is something that perhaps you can discuss with Martin.
I have a question connected to the chronography. I don't know how to say this in English, of the universe. So, is the age of the universe different in this model?
No.
Is the
overall age is the same, but there's a stretching by a factor of 2 at the beginning, and then there's a corresponding slight compression towards the end.
So should we able to test your predictions also using the age of the galaxies, for example?
Yes.
So if we go back in time, should we have enough resolution to see difference?
Yes. So both of these have now been analyzed in the context of the timeline. One is the age of the supermassive black holes, and the other one is the appearance of these redshift 10 or even 12 dwarf galaxies that are being detected now. The problem with the galaxies, as you're pointing out, is even worse than with the quasars, because with the quasars you're talking about one object, and you can imagine some exotic catastrophic event that created them, right, because it's one object. But with galaxies it's more difficult because you're talking about 10 to the 9 stars, and those 10 to the 9 stars had to be made from a redshift of 12 in only 150 million years. From the time, population 3 stars appeared to the time these dwarf galaxies emerged at redshift 12. So we're going from redshift 15 at the end of the dark ages to redshift 12. There's only 150 million years to do that. So somehow these 10 to the 9 stars had to be made in such a short period, just from population 3 stars evolving into population 2 stars. So there's a significant timeline problem, probably even more with galaxies than there is with quasars.
And do you have, just to put this in numbers, an example of how much is the difference in time between, let's say, the beginning and redshift 10 compare in your model versus the standard model?
Yes, so it's about a factor of 2 up to a redshift of 5 or 6. So the dark ages, instead of being at 400 million years, would have ended at about 900, and then a redshift of 6 goes from 850 million years in the standard model to about 1.9 gigayears with this other zero active mass picture. So it's almost a factor of 2, all the way up to a redshift of about 5 or 6. By the way, while we're here, we're going to be talking about another observation, a third possible problem with the timeline in the standard model, having to do with the Lyman alpha emitting galaxies and the carbon-4 absorption systems. These pairs have been seen at several redshifts, but there's now one at a redshift of 5.7, I think, which creates a problem with the standard timeline because, as we understand it, the metallicity to create the absorption system was brought out there by the supernova ejecta, the winds created by them. So according to standard astrophysics, there's a finite amount of time needed to bring the C4 system out to the distance that's seen, and that is too far, according to the observations, for how much time is available in the standard model to make that work. So instead of making that a pair, the solution in the standard model requires the introduction of an unseen dwarf galaxy at the location of C4, which again is one of these, ad hoc solutions where you introduce something that's hidden in order to explain something that doesn't fit in the standard timeline. Go ahead, Nacho. Yes, yes. Yes, is also very different. Very good, yes. So the Big Bang nucleosynthesis is an entirely different topic, and we didn't get into that. But just to keep it as short as possible, the biggest problem with BBN in the standard model is the lithium anomaly, right? So when we say that the standard model accounts for BBN, that's actually not completely true, because it doesn't predict the helium abundance. We fit the helium abundance in order to be able to predict all the higher elements like lithium. But lithium-7 is the only one that's measurable with any degree of certainty. So in the standard model, when we do BBN, we use the measured fraction of helium to fix the initial baryon photon number and the temperature and all those other conditions, and then we do the calculation, and the only thing we really predict is lithium-7. We also predict lithium-6, but that's more difficult to measure. And lithium-7 misses by a factor of 5. It's the so-called lithium anomaly. So the standard model does not explain BBN properly. It misses by a factor of 5. In this context, with zero active mass, the way BBN would happen is quite different. Instead of having all of the burning happen during the first 18 minutes while the neutrons are still alive, it happens over about 120 million years, because weak interactions sustain the neutron population over that time. So the burning happens quiescently. Instead of all happening catastrophically in 18 minutes, it happens gradually over 120 million years. But because the physical conditions are more gentle, the lithium is not overproduced. So actually burning with this context does away with the lithium anomaly. It removes this factor of 5. So BBN actually works better with this steady expansion than it does in the standard model picture. But yes, also the CMB happens at a different time. The CMB would have to be produced at a redshift of about 26 instead of 1080. And it's not inconsistent with any of the other observations that we have, but that's quite a big difference, it's true. There might be some interesting observational consequences of that, because going from 1080 to 26 is quite a big change. So that's something to look to, because that might be the signature that is perhaps the most significant.
Okay, final questions?
So, from your point of view, what would be what do you suggest, or what test do you suggest in order to prove or to distinguish in this situation, to distinguish between standard model and SAMs and so? Or what would be the set of tests good enough to clarify this ambiguity?
Right. So there are several different observations that can be made, but I have to point to Nacho, who last year actually suggested, I think, the best test that one can do, which is Redshift Drift. If it's possible to identify lines, like in AGN, say, that are very stable over, say, 20 or 30 years, then we can measure the actual redshift drift. Because in the standard model, since the medium is accelerating or decelerating, we think it's accelerating today, then there would be a redshift drift associated with that local acceleration, whereas in a zero active mass situation, there's no acceleration, so the line should stay fixed over a 10 or 20 year baseline. And there's a possibility of maybe having observations with SKA or other surveys that are coming up over the next 20 years of doing this. And estimates have been made. One can get a difference that corresponds to about 3 sigma in 5 years between steady expansion and the accelerated expansion in the standard model. So it would be 3 sigma in 5 years. Maybe that's optimistic, but this is what's being predicted. And the difference would be as much as 5 sigma, which at that point then becomes very compelling over a baseline of about 20 years. So if everything goes well, and maybe this is overly optimistic, I don't know, not sure you're in a better position to judge than I am, but if it's all feasible, then maybe in 20 or 30 years we would have a 5 sigma confirmation one way or the other. That's probably the best test, I would say, because it's fairly clean. It doesn't depend on, you know, extraneous factors, but it does require the identification of stable lines, though. So.
Yeah. Thank you very much for your talk and answering a lot of questions. So Fulvio will stay another few days at our institute, so just come to his office at Orion, close to GTC. Thanks again, the speaker.
Okay, all right, thank you. Yes, we went over time. I'm sorry about that.